Oh, you know what? I did promise that we'd allow a couple of minutes for any questions that arose. So before I go on, let me ask for anyone who was here yesterday, following along, or maybe you decided to be of the intrepid sort and go ahead and try out some of the tools after we were done. Does anybody have any questions about kind of the general getting around Inspire, setting up an analysis, or taking a look at the results of an analysis? Oh, and I see something has popped up here. Please share the link to the exercise files. Okay, so that's on Darius. Okay, okay. Okay. So any questions about anything that we covered yesterday? Okay, yep, okay. So obviously, if you have any questions that you think of, don't hesitate to pop them into that chat window, and we'll get to them. But barring anything left over from yesterday's session, let's hop right on today's. Okay, so what we're going to talk about today, or what we're going to start out talking about today, is geometry creation and model simplification. And just like I said yesterday, we're not going to focus on PowerPoint. If you've downloaded the files, you are aware of the PowerPoint that's in there, and please avail yourself of that. It's a great reference tool for looking back and seeing some of the things that we've done, but we're not going to waste our time looking at pictures. We're going to deal entirely with the model, or using the software. So before we get into geometry creation and model simplification, we need to understand why we're doing what we're going to be doing. So analysis is very straightforward. We wanted to take a part, we wanted to set it up, we wanted to simulate the situation that that part was in, and we want to see how that part behaves. No different than doing a full-blown analysis with a full pre-processor and solver and post-processor like HyperMesh or some of the other products that are out there. But HyperMesh, OptiStruct, and HyperView, you could do the same thing. And the idea then is to just take and understand how our part behaves. We need to know how much it deforms. We need to know what kind of stress. We need to find out some information about our part. So that's very straightforward. But now what we're going to move into, and the reason why I discuss this before we get into geometry, is because most of the functions in geometry are for preparing an optimization. You can absolutely create everything you want from scratch in Inspire, and Inspire has some tremendously powerful geometry creation and editing tools built into it, but it is not a CAD system. It's not designed to be a CAD system. I think it becomes more and more CAD-like with every release. But if you're an expert in SolidWorks or CATIA or UG, all your CAD work can be done in there, and then we can bring in the geometry into Inspire. And we can create and edit geometry within Inspire. And most of what the editing tools focus on is the creation of what we call a non-design space. So we need to understand the idea of a design and non-design space in optimization. So a design space and optimization, what topological optimization does is very much like sculpting. So I have a little block here. I just created this little block. And 500 or so years ago, Michelangelo made a statement, something to the effect of, and far more eloquently than I can say it, but something to the effect of, in every block of marble, he sees a statue, plain as though it was standing there in front of him. And he has only to hew away the material that imprisons that lovely statue to basically reveal it to the rest of us. And what he's saying is, if you take a look at a block of marble, and we're going to pretend that this is a block of marble right now, the only thing separating this block of marble and a statue is the extra material around it. So if I can come here and hew away this extra material, I get a statue. Now mine isn't as eloquent as Michelangelo's David or Pietà or anything like that, but I can create a little Darth Vader statue by getting rid of the extra material from my original block. So really, if we think about it, the statue already exists within the material. All we have to do is get rid of the extra material, the material that's not part of the statue, and the statue's right there. So what does this have to do with optimization? Well, interestingly enough, and if you remember, let's bring up desktop, here, models, finish models. Let me grab this right here. If you remember what we did yesterday, we had this part. Let me get rid of these. Let me hide these shape controls. We had this part right here, a big block of material. And from that block of material, we got this optimized part. What's the difference between this and this? Essentially the exact difference between my block and my little Darth Vader statue. Getting rid of the extra material. That's what topological optimization does, and that's what Inspire does. Just like a sculptor, you give Inspire a block of material, and from that block of material, it carves out not a statue, but a part. And while the sculptor carves a statue out to make it beautiful, Inspire carves a part out to make it practical. And I discuss this because that's where we're moving on to. We need to understand the idea of the design space, the block of material. That's what we want to create. And just like a sculptor wants the largest, nicest, most perfect block of marble or wood or whatever to carve their statue out, we want a nice big block of material from which we can carve our part. Now you'll notice here that the section of my part that my design, my optimization was carved out of is in red, but these parts are in gray. This is its own solid. And this is the design space. The design space is your block of marble that's going to become a statue. It's what Inspire is going to carve away at. But if this part is going onto a vehicle or going onto something and it's going to be mounted through these holes right here, we absolutely need those holes to be there. They can't be removed. They can't be carved away. We have to have a nice perfect cylinder for, say, a rod or a bolt to go through. And that's why we separate them from the design space and establish them as non-design space. Non-design space is the material that Inspire won't touch. Mounting areas, loading areas, this flat plate down here, we want a nice flat plate to mount onto the vehicle or mount onto whatever, another flat plate back here, and then these holes. These are what we describe as non-design space, the material that Inspire can't touch. And so what we're going to do is, using a combination of simplification tools and geometry creation tools, we're going to take and create this design and non-design space, potentially off of the part that we just ran our analysis on. So before we move any further, let's just make sure, are there any questions about the idea of design and non-design space? I do see a question here. Let's see. What do we have? No? So we good with not design and non-design space?
Looks like we're, no questions there. So
Yep. Let's look. Okay, excellent. I keep getting this little question thing, but it's just people responding to yours. Okay, cool. Okay, so then let us now take a look at the geometry functions within within Inspire, and we're going to focus, of course, on the geometry ribbon, and we're going to talk about all these little features running down the line here. So let me come here, and I'm going to start with just a brand new section. I have nothing in here. So these tools deal with geometry creation. Now keep in mind, if you're a CAD user and you can use CAD, by all means, create the file in your CAD. This Parasolid, for instance, was created in a CAD system other than Inspire. Well, I could create this in Inspire. If I were a proficient CAD user, I probably could create it a little quicker in my CAD system. But if push came to shove, I could absolutely create it in Inspire. So the geometry creation tools deal with these 4 icons right here. Do I want to create lines, rectangles, circles, or arcs? And Inspire uses a rather unique creation technique. I draw a sketch. So I'll click a rectangle. Now you'll see there's 3 different options for creating a rectangle here. And the icon clearly shows which one of those 3, or which each of those 3 options do. The one I selected is the corner to corner. So I pick a corner, I come to another corner, it gives me dimensions. I'll say I didn't want that 90 millimeters, I wanted it 80. I can just type in 80, and this one I didn't want 130, I wanted 150. Or maybe I wanted it 4 inches. So I can type in the value. I can be very accurate about dragging it, or I can just roughly drag a rectangle and put in the dimensions I want. Once I have those, I can right-click to get out of the creation mode. And now I still have my sketch. I could continue sketching on this, or I could right-click again, and Inspire puts me into what we call the push-pull mode. With the push-pull mode, I can grab that surface and I can drag it up. Put in the exact dimension. And now I have an 80 by 150 by 80 block. Now say I want a hole through this. Well, I can come to my hole. I'll pick the center and radius. I indicate what face I want to draw this on. So I'll indicate that face right there. Indicate the center, drag a radius, and again, I could type in a value here. 40 I didn't want. I want to say 35.75. Type that in. Right-click to get out of the sketching. Right-click to get into push-pull, and now I can drag that and drag it out, and I could put a little cylinder on it, or if I drag it in, you notice I cut a hole right through that. And I could come here and put a hole on this face right here, right-click, drag that through, and now you see I get these intersecting holes going through the inside here. So you can see creating geometry in Inspire is relatively easy. If I wanted to, I could, let's see, we'll come to polyline here. I'll sketch on this face, and I'll come from here to here to here to here to there. Right-click to get out of that, and right-click to get out of that. And now I could take and drag that through and drag that through, so I can put shapes on my faces. So anytime I sketch on something, I can drag it or pull it, cut through my existing geometry, or add to it. And I can do points and lines, rectangles, circles, arcs, If I have lines, I can trim and break my lines. Patch is used if you're bringing in geometry, and for whatever reason, I didn't quite recognize it as an enclosed solid, and patch allows you to patch up a missing surface. Doesn't happen often. In fact, I've never had geometry that happened to, but it's there in case you need it.
Eric?
And yeah.
Question, is there a way to position the hole at an exact distance from an edge?
There is not a way to say I want it at an exact distance from an edge, other than to just know where that edge is located. So, you know, if I come here and I grab a hole and I come out of here, you know, I know my edge is up here, and each one of these is, I believe, a millimeter. So I could do a graph, you know, on a graph like this. But there's really not the ability to position it exactly. If I wanted it, you know, 34.725 off of that surface, it would be, you'd end up having to create a point at that location, and it would be difficult. Remember that the idea here is not to, I mean, it's to create geometry, but we're definitely not a CAD system per se. So you're going to find a lot more convenient tools for creating geometry in a CAD system than you will in Inspire, especially if you're looking to kind of do more advanced stuff like that.
Thank you, Eric.
It is kind of cool, though. Yeah, no problem. And would have gotten to this, but we'll start right here. If I come to move faces and I pick a face, I can actually take and shift that hole and move it off of location. But again, it's just this value right there is off of its initial location. Okay, so we've already discussed the push-pull. I can enter push-pull after a sketch, or I can click on the push-pull, grab a face, and move it. If I hold my shift key down while I push-pull, I'll actually pull a new solid. So what ends up happening now is this is a new solid. This is particularly useful for creating things like non-design space. Say I want this face, I need a non-design space on this face. I can come to push-pull, grab that, hold my shift key, drag it out, say 2 millimeters, and now I have a separate solid there that can be non-designed. I can also push-pull rotating. So if I come to here, I grab this face, I click what I want to rotate about, and then I can rotate that. And you see it carries the hole along with it. And just like with the linear push-pull, if I hold the shift key down, I can push-pull a new solid as well. We already talked about moving faces. Mirror is quite simply a mirror. I select a face that I want to mirror on, and it will mirror it. If I need to do two parts, I need to select one and Control select the other, and then come to mirror, indicate a face, and it'll do two. If I do not select the parts in advance, it will just mirror the part that has the face that I applied the mirror to. Scale is scaling. Oh, and on mirror also you'll see that I have the ability to keep the original. If I turn that off, it gets rid of the original part. Scale is scaling. If I click a body and I say 0.5 scale, It's at 0.5 scale. Boolean operations are the same Boolean operations that that everyone's familiar with. I can do a combine. I just pick two things and it will combine them. If I do a subtract, I pick my target, I pick my tool. Well, it would help if I hadn't combined those. Let me undo. There we go. And we'll do a scale, 0.5. There we go. And now let me come to Boolean, subtract. I pick my target, I come here, I select my tool, and it will give me a preview of what that subtract would be. I can also select keep tools, and now it looks like it did before, but if I come here and I hide that, you see that that has been subtracted out of the original part. Let me undo that, because I also need to demonstrate intersect. So intersect, I pick a target. Let me reset that. I pick a target, I pick a tool, and it calculates the intersection of those two. And if I were to click intersect, that's all that would remain is that part in red. But I can also keep the target or the tools. Cut allows me to cut apart. It is by far my favorite icon within Inspire. You see we get this little buzz saw. And if I select a solid, it puts a cut through that as soon as I click cut. And now I've got two separate solids here. One other nice feature is cut will adhere to snaps. And we have snaps on centers, snaps on ends. And so that means if I come here, I could select the mid and cut that part exactly at the midpoint. I'm going to skip simplify just because I want to use that tool on the part that you're actually going to be working on the exercise. And I'll skip partition as well, because that's going to be on the exercise too. And I'll just come over here to fillets and chamfers. Fillet, I can pick an edge. And we'll add other edges to it. And you see as I do that, it wraps a nice fillet around there. And you see as I add other edges to it, I get a very nice looking fillet, rounded corners. I change the radius. And then as I fillet, it gives me that nice fillet there. Chamfer works the same way, except it puts a linear chamfer on there. Depth, and then the angle at which it cuts. So these tools are for editing your current geometry. Again, nothing revolutionary from what you can do with the CAD software, but it saves you the trouble of having to go back and forth between the CAD software. Now, where the true power of Inspire geometry comes in. Oh, let's do this. Let me open up this one. So this is where you should have been at the end of the last exercise. We ran an analysis on this. We know how this thing behaves with both of the load cases. But now we want to optimize it. Somebody went through and did some optimization on it. They put these little pockets in there in an attempt to save weight. And that's great. The traditional way of optimization. Usually it's just based upon experience, or maybe you run an analysis and where there's not much stress, you poke a hole in it. But that's not intelligent optimization. Inspire is going to do intelligent optimization for us. Just like we saw with that initial part, Inspire is going to carve away the material, as much material as you specify, but leave and make sure that the material that remains meets the criteria that you set forth. Gives us the maximum stiffness or the minimum amount of mass. Meets structural requirements. Meets manufacturing requirements. All of these things are what we do with optimization. But to be able to optimize this part, I need to make sure that my geometry is in the best shape possible to optimize, and this is not. If I were to optimize this, it would be the equivalent of a sculptor picking out a statue and carving another statue out of it. You very, very limited what you can come up with if you're carving a statue out of a previous statue. So I'm going to be very limited as to the parts that I can have if I try to optimize out of this part. What I instead want to do is give it the biggest block of material I can. So what you effectively do is determine your design volume. How much space, how much volume do you have for your part to exist in? And you want to fill up that volume with material so that Inspire can create the best part possible that fits within your design space. So the first thing I'm going to want to do is fill in these pockets here. I don't need those. And to do that, I'm going to come to my Simplify tool. With Simplify, what I can do is I can come to holes. It's going to identify holes. And if I pick on one of them, it gets rid of it, which is something I didn't want to do. And if I click Remove All, it would get rid of all of them, which again is something I really don't want to do. What I do want to do is get rid of these pockets. But unfortunately, it hasn't found them. But all I have to do is double click on the bottom of the pocket and automatically selects all of the surfaces around it. I click again and it fills it in. And this is where the geometry tools in Inspire shine. This is why I say we're not necessarily keyed for creating geometry, though we can do it, but we are absolutely fine-tuned to simplify your geometry and create design spaces. This has to be much easier than it would be in a CAD system. To be able to just double click and then click one more time and get that. Now we have these angles here. If they're necessary, if you have another part coming in, then they'd have to stay there. But if they're not, I want to create a nice big square, big cube. And if I come to push-pull isn't just linear. Push-pull, if I grab this, you see it follows the geometry, and I can pull that to a sharp point. Come to this side, pull that to a sharp point. Come to the back, pull that to a sharp point. With Simplify, I can also remove fillets. So we showed how we could create fillets, but with remove fillets, it will identify all the fillets, and then I can click on them and remove them. Now this pocket here, this pocket is probably there for a reason. I could remove the fillets on it if I wanted to. but I want to make sure that that pocket stays there because this is probably seating over something. So now you see, now I have an ideal design space. It's a big block of material. One other thing with mentioning, we're not gonna use it here. Plug and hole work pretty much the same way. If I come to hole, you see it fills that in. Plug will fill it in as well. But what plug does is it fills it in with another solid. So it's kind of like a negative volume creation tool. Okay, so any questions about geometry simplification? Okay. So what now? Well, we're not quite ready to move on to optimization, but we're getting there. What I want to do now, though, is I've got some features on here. In particular, this mounting hole right here where the door is going to hang off, and these bolt holes where it's going to mount to the frame of the mount to the airframe. Those have to be there. I can't exactly optimize away the hole that the door hangs off of, or I'm not really going to have a very useful door hinge. So what I need to do is I need to make sure I have a non-design space solid around this. So I come here to my partition, grab my hole, tell it how much I want, maybe 4 millimeters. That's a good non-design space. Right click, and you see now I have a separate solid. And if you remember, if I come here to contacts, you'll see that that separate solid is bonded to my part. Any two solids that are in contact to each other are automatically bonded together. Now, to make sure that these holes down here stay, I again come to geometry partition, but you notice how it not only recognizes the hole, but it recognizes the pocket. If I select that, it actually will create this entire non-design space. Well, I don't need that. I don't need the whole thing. I don't need to protect this pocket. That pocket is there so I can have access to my bolt head. And since there's no geometry there, no matter what with the optimization, when that's done, I'm not going to have geometry there because Inspire topological optimization is subtractive. It is never additive. Just like I can't have a statue that's larger than the block of marble I started with, I can't have a part that's bigger than my design space. So that pocket needs to be there to guarantee I don't have material there, but it doesn't have to be protected. So what I'm going to do is I'm going to actually do control click. I'm going to remove that surface there. And now if I select that hole, I just get what I need, which is a cylinder around the hole. And I can now go through and do it to all 6 mounting holes on my part. And after I did that, I would have the perfect design space. And then all I would need to do is right click on it and select that as design space. And then that gets carved away when I do my optimization, which is what we'll describe next. Any questions?
Eric, can you repeat how you did that control click again?
Absolutely. So I can come to here. I'm going to come to partition. It has identified this whole pocket. If I hold my control key down, you see my pointer modifies to have a minus on it, all I have to do is left click on that surface. It's no longer selected, and since they're no longer connected, when I grab that, it will just do the hole. And then when I right click out, now these are non-design space.
Thank you.
Okay. Mm-hmm. So this is my goal now, is to create this big, bulky part and let Inspire do its job and carve away the material. The more material I give it initially, the better the design of my part. Okay, if there are no questions, if you come to, where is it at? There we are, page 94. We have a 6-step exercise on simplifying this part. Every time I import, this is a question, let's see here. Every time when I import an assembly from a CAD program, Siemens Inspire is summing several parts up into one. How can I change to prevent it? It shouldn't be doing that. It should maintain the integrity of your original assembly. What version of Inspire are you using?
If the student version, it's 27.1. I mean 27.1.
Oh, okay.
But I'm not sure if he has a student version.
Okay. Yeah. So I would definitely make sure you're using the latest version. But lacking that, if there's if you can post your question on the forum and then use 2016 and not the student version. Okay, you can try it in 2017. Obviously maintaining the latest version is ideal. If you are a
competitive
if you are a team, you can contact your whoever your Altair representative is. Ideally, if you can get them the model, they can take a look at it, because Inspire is supposed to maintain the integrity of your CAD model, which means if you had separate parts in your CAD model, Inspire should be maintaining that as separate parts. So if you can get them your CAD model, they may be able to take a look at it. No problem. Okay, so if you want to take a look at that, page 94, work through that exercise. We'll give you 15 minutes to do that. At 4:30 Eastern time, we will pick back up and sum everything up with going through how to set up the optimization, running it, and interpreting the results, and we will then call it a day. So work on that, and then we will pick back up at 4:30. Okay, so where we are now is moving on to optimization. We've got everything set. We've got our model prepared, the load cases set on it. We've gone through and we've worked out all of the design and non-design spaces. Let me grab that model right here. Models, exercise 7. So you should, whoa, that's not what we want. That's what we're going to get. Let's go back to there we go. Okay, so this is, that is our model as we've got it. So what we want to do is we want to set this up for an optimization. So let me get rid of that for right now. Excuse me, sorry. So we've got all of our holes partitioned out. We have our constraints on there. We've got our 2 load cases. This is the same model that we ran the analysis on, but we went through and worked on the geometry so that we have an ideal design space. And we right-clicked on that and set it as design space. To indicate the design space is nothing more than just clicking on a solid and selecting design space. Once we have that design space set, we're technically ready to run an optimization. But this bracket right here, there is a possibility, you know, say this aircraft has doors on both sides of the fuselage. And we don't want to have custom brackets, custom hinges for each side of the airplane. So we want to use the exact same hinge on both sides. So I know that if I take this and I rotate it and put it like this, the part can be the same on the other side of the aircraft. The problem, though, is in the act of rotating it like that, you see now my door force is pointing up. So what I actually want to do is I want to make sure that my part is symmetrical. Because if it's symmetrical, then it doesn't matter which way we put it on. What happens with the symmetry is it runs the analysis, it runs the optimization. That force that's pulling down on it right here is going to force it to put material here to account for that. And if I just left it as is, I'd have a lot of material down here and not much up top, because this is where the force is going to be acting. But I want to make sure I have a symmetrical part. So by putting a symmetry plane in there, anytime it puts material down here to account for the force going down, it's going to put the same material up here, which effectively guarantees that my part will be symmetric. And to do that is really easy. All I need to do is come to my structure now, and I come to my shape controls and grab symmetry and pick the solid I want the symmetry on. There are 3 possible planes of symmetry, and currently all of them are highlighted. But what I'm going to do is I'm going to come and left click on that plane and left click on that plane, leave only the plane running down the center. And now that guarantees that my part will be symmetric across that plane. There's another type of shape control, and it's what we call manufacturing constraints. Let me talk about what manufacturing constraints are, and then I'm actually going to go back to the slides for just a minute, because there's some relatively decent pictures on there that kind of highlight what manufacturing constraints are. But if you imagine this, I am going to set up Inspire, and I'm going to run an optimization, and I'm going to have Inspire create for me the most incredible part that has ever been designed in all of history. It weighs next to nothing. It's stronger than anything that's existed before. It's dirt cheap from a material standpoint. But if I can't manufacture it, then it's useless to me. The best part ever designed in all of history is entirely useless if I can't make it. And this is becoming less and less of an issue, primarily because of the advent of additive manufacturing, or as we tend to call it, 3D printing. 3D printing allows us to create parts that we never would have dreamed possible even 10 years ago. The traditional manufacturing is either stamping, casting, or molding. And there's also, of course, machining away. But typically, we don't just machine away from nothing. We start with something. So stamping, casting, and molding. The thing about stamping, casting, and molding is it does require a part to meet some certain requirements. And that's why I'm going to come back here to the slides, because I think this slide kind of demonstrates that relatively well. So without any constraints, manufacturing constraints put on there, and this really is a bad picture because it really doesn't show it, but if you could see it, what you would see is this is entirely hollow on the inside. And that's a really good structure. Hollow on the inside, nice shell on the outside to provide it rigidity. That's great. But it can't be manufactured. So what we need to do is add shape controls, and I'll show you how to do that in a second, but we need to understand what they are first of all. We have single draw, split draw, stamping, and extrusion. Single draw and split draw are for either a stamping part, a stamped part, or a cast part. And what you can see from this little cross section here is if I'm creating a casting, for instance, I need to make sure that my part can be removed from the cast. So it needs to not undercut. And by selecting single draw, you see that my part now has these kind of internal ribs in it. So I can imagine I could pour this into a mold, turn the mold over, smack it, and this would fall out. Split draw works the same way, but it's as if I bring two molds together, which allows them to come out at an angle, but only at the split plane. Stamping works just like the single draw, but it tries to guarantee that you get a continual thickness part that you could use to design a stamped part from, as opposed to a cast part. And then extrusion, what extrusion does is it guarantees you have the same cross-section running all the way through. Even if your ultimate goal isn't to extrude the part, maybe you're going to laser cut it or water jet it. Laser cut and water jet, even though they're not extrusion processes, they still guarantee that you have a part that has a continual cross-section running through it. The extrusion constraint works that and well in that. In this particular part, I'm not going to inhibit it with a manufacturing constraint. It's aerospace, so it's relatively low volume, so I can go ahead and 3D print it. So I'm going to just put the shape control on there and leave it to go. That's all I need to do now. And now I can come to my optimize tool here, and I can run the optimization. Now, I'm not quite ready to run it. I need to set some parameters first. So once I click the run optimization, I get my optimization window. I can put in a name. I have the option of maximize stiffness or minimize mass. Those are the two excuse me, types of optimization that I can run within Inspire. Maximize stiffness allows me to specify an amount of material that will be removed, and the optimization will guarantee that the material that remains provides the stiffest part possible. So with maximize stiffness, I get this little bar here, and it defaults to 30. That's the amount of material that will remain after the optimization is done. 30% of the material. So 70% of the material will be removed. I can alter that between 5 and 50 using the scale, or I can set a manual amount right here. Just bear in mind that this is the percentage of material that will remain after the analysis is done. Next, I can set frequency constraints. I know that on this helicopter, there is a certain resonant frequency due to the engine running or the blades turning, and I want to make sure my part doesn't vibrate at that. So I can maximize frequencies, or I can set a minimum frequency to the 10 lowest modes. And then I can do it either as free or supported. I can set thickness constraints. And for that, let me see if I've got a good picture on here. Only because I don't want to have to go to, there we are. So thickness constraints determine the minimum thickness, determine the minimum thickness of any little feature that is created within here. A thicker minimum thickness will guarantee a more defined part. Maximum thickness works the other way around. It dictates how thick any particular feature is. Minimum thickness, the higher you make it, the quicker your analysis will run. Because the higher minimum thickness you create, the larger the element size it can use. Your element size will typically go to 1/3 of your minimum thickness. So try to be realistic with that. Speed versus accuracy again. Contacts. Contacts deal with the contacting surfaces. Bonded surfaces are always stuck together. But if I have contacting surfaces, I can allow them to separate. By default, think of it as two really strong magnets put together but oiled in between them. So I can kind of slide them back and forth, but they do not want to come apart, nor will they pass through each other. I can specify sliding with separation, which will allow those to part, but not go through each other. Selecting sliding with separation can significantly increase the runtime for your analysis. So only use sliding with separation if you're truly expecting it to separate. And just like with the analysis, do I want to include gravity and which load cases do I want to include? When everything's set, I click run. My other option, minimize mass. You see, minimize mass, I lose that target. So now with minimize mass, I actually do not say remove this amount of material. Minimize mass will remove as much material as it can while maintaining a factor of safety. So you can put in a factor of safety here, which is it takes the yield strength of the material that you put in the material card and divides it by your factor of safety and sets that as a stress limit. So I can either do minimize mass or maximize stiffness. A lot of times people will do both and kind of take the ideas from both of them. One thing that you can do with minimize mass, let me close this, is now we can put what we call a displacement constraint on there. So say I come to here, and I do not want the center of this hole to move more than 2 millimeters in any direction. I can come to displacement constraint, pick the center of the hole and say 2 millimeters. And you see that little sphere that it created? That represents the maximum that that center of hole can move. And now that will be taken into account in my minimized mass analysis. And then I click run. When my analysis completes, I end up with a part that looks like this. So what we'll do is we'll break now, let everyone go to exercise on page 111. It's a pretty quick exercise. You just set the symmetry plane and then set up the optimization. So follow those. Set up the optimization, run it. We'll do 13 minutes, so at 5 o'clock my time, we'll pick back up, take a look at the results, and see where we can go from the results. So run your optimization, and then we'll talk about the results and wrap it up for the day. Excuse me. At the end of your optimization, you should end up with something that looks a lot like this. If you need to get back and forth between your original design space and your optimization, you can always click on the body and select design or the topology min-mass, or you can come over here to your model browser and select the design or the topology. Any optimization that you run, as Darius had mentioned, he ran it both ways, probably maximize stiffness and minimize mass. Any optimization that you run, any iterations that you run will all be saved in this same model, and you'll see a whole list of all of your options right there. Now, when we've got this up, what we can do is once we have the topological shape, we can take a quick look at it. If we notice that some of our members, you know, maybe a little thin, we're a little overzealous, we can always use this Shape Explorer to add or remove material so that we can get a good shape. When we're happy with the shape that we've got, what we typically want to do then is go into Analyze. This is telling me I've got a good shape. It is optimized it. You can see it's substantially lighter than the original part, but I need to make sure it works. So I get it in the shape that I want. I click Analyze. This shouldn't take too long at all. It will take the exact shape that I have, it will remesh it, and it will run an analysis on it based upon the parameters that I set, or based upon the loading conditions that I set. And this analysis should look like any other analysis. As soon as it's done, we get the little flag there. I click that, and now we can see, and I can run the analysis. And I look at the vertical and the lateral loading, and verify that my part meets my requirements. So everything right here within Inspire, I can do from running the initial baseline analysis to running an optimization to analyzing the results of that optimization. Now, Inspire, as I kind of mentioned at the beginning of this whole endeavor, is not a push-button get part program. It's not designed to replace you, the engineer. It's designed to provide you the information that you need to create the best parts possible. And Inspire has done some interesting things here. It has completely eliminated these two mounting locations. It is determined that they're superfluous. They're not necessary. But maybe I have FAA requirements that say that this has to be attached in 6 locations. Well, then I would manually design that. But the question then is, how do I get this information out of Inspire and into some sort of useful format? Well, that's where this little button right here comes along. And we actually have a couple of different options. I can click Fit. And once I click fit, what's going to happen is it's going to, let me close my mail here. You definitely don't need to be getting little mail pop-ups. It's going to go and wrap surfaces around my geometry. And when that's all done, let me open that up. It falls under the optimization category for whatever reason. Excuse me. Give it a second. Nothing like sitting and watching a little ball spinning here. But once that's all done, it will take and it will put nice smooth surfaces wrapped around this. And I can export this as an IGES, a Parasolid, a step, or an STL file. So these are now surfaces, and I can just come here and select Save As, and save it as an IGES, a Parasolid, or a step,
Eric,
or an STL.
Also export the non-design space with it too?
Oh, yes. Yeah. So it has wrapped geometry around everything. So all solids here, or all my part and my geometry and my non-design space has had geometry wrapped around it, and that will get exported.
Thank you.
Yeah. Because actually, in this shape, my non-design space is still being represented as geometry. There was, until I wrapped geometry around my optimized shape, there was no geometry there. So the non-design was already still representable by geometry. So you will get everything out of there. And from there, you can import that into a CAD system, and you can use this as a framework for developing your part. There is another thing that we can do, and this is relatively new, and this is kind of where we start moving away from the science of FEA and almost move into kind of an art of FEA. The one feature we never talked about was this little guy right here, PolyNurbs. PolyNurbs is a new addition to Inspire. And the cool thing about PolyNurbs is it allows us to actually create geometry to match our part right here within Inspire. And using PolyNurbs, what I can do is I can come here to the PolyNurb, and if I select this wrap option here, what I can do is come over here, and you see it automatically recognizes the cross section of my part. And I can come and drag this NURB, and it puts this PolyNurb. A PolyNurb is a solid whose shape is driven by a cage. So it creates this cage here. And what I can do is come to each one of these legs and generate this solid geometry. And I'll come to each one of these legs here and generate that. And then I can begin to bridge these together. So I could come to here and maybe bridge this to that, and bridge this to that. And now that I've got those bridged, I can come and bridge this over here to that, and bridge that across there. And you can see I can begin to generate this geometry. And the geometry, I don't even have to wrap surfaces around. This geometry is exportable as a solid directly into a CAD system, and I don't even necessarily have to then use the CAD system to create my part. I can create my part using PolyNurbs right here within Inspire. Now this part is definitely kind of an advanced model. Just check to see what the So that's chapter 8. Let me grab the chapter 8 model here. Exercise 8A. This is a much easier model to do the polynerbs with. And you'll see with the polynerbs, what I can do with the wrap is I come and I create these tubes for each one of the legs. And then once I have these legs set, then I come to the bridge, and I bridge from here to there, and I get that, and then I can bridge from here to there, and I get that. And you can see I can create these solid shapes. And the neat thing about polynerbs is what I can do, since they're driven by these cages, I can force my geometry to very highly adhere to my cage, or very loosely adhere. So I can get these nice kind of edge-rounded rectangular shapes. And right here from within Inspire, I can create my part relatively easily. Using this bridging and the wrapping, and then the sharpening. And right there, you can see that's a pretty slick looking part. Let me keep those polynerbs on. I'll turn off my, all right. So there you go. And relatively quickly, I could go around the part and create that. And these are solids. I could right here say File, Save As, and export this directly to and hide just a parasolid or a step, and have the part designed right there. Can topo optimize if you exported an STL? Oh, no, wait a second. There it is. Is it possible to use those tools, polynerbs, with standard optimization process, hypermesh, OptiStruct? I guess yes, in that you could save your shape, and then we do have the ability to open, as you see here, a OptiStruct FEM file. So I can bring the FEM file in here, and then I could do the polynerbs within Inspire. So polynerbs are unique to Inspire. We don't have them in hypermesh, but I can bring that FEM file from my optimization into Inspire, and then do the polynerbs on it. Once the FEM is solved, it's not an FEM, it's an H3D. Actually, when you're in HyperView, let me get HyperView. I know we're kind of going a little bit off topic here, but that's perfectly fine. So yes, it is an H3D. But in HyperView, when you've got an H3D file, what you can do is come here and say export as solver deck. And obviously I don't have a model loaded, but once I do the export as solver deck, I can actually export the shape of my part. It's used to export deformed shapes. So if I've deformed a body and I want a mesh of that deformed body, I can deform that. But it also works great with optimization. So I can export the shape. It'll be an FEM file. I can bring that directly into Inspire, and then have some fun wrapping NURBs around it. Excellent. Also, OS Smooth should work for that as well too, because I believe from OS Smooth you can, and OS Smooth actually, now that I think about it, you have to give it a try with HyperView. I can't remember whether HyperView is going to do it as TETs or whether it's going to do it as triads. If it does it as TETs, you're good. If it does it as triads, you're not. You may have to use the OS Smooth function for that, and OS Smooth allows you to export an FEM file as well. So one of the two will work, and then you can bring that right into Inspire. So that's it. We have started with Inspire. We brought it up. We discussed the interface. We understood how to get around in Inspire, understood the concept of the multifunction icons, the ribbons, bringing geometry in, setting up an initial analysis, getting those constraints, those load cases, all that sort of fun stuff going, getting an analysis run, taking that geometry and converting it into a nice design space with non-design spaces as necessary, setting up the optimization parameters, running our optimization, looking at the results of the optimization, reanalyzing those results, and then potentially even creating NURBs from it. And that's it. I know it's been a little bit rushed. Normally, you know, in a normal class, we go for about 6 hours or so. A little more, some more time for exercises, some more interaction. But hopefully this little class has given you the basics that you need to kind of go forward on your own with Inspire. Get your hands on that student version. Take a look at Altair University for some videos, for some self-paced training, for all that sort of stuff. There's also some excellent tutorials right there in the Inspire help. Have some fun with it. You will be amazed at the things quite quickly you'll be able to do with Inspire from an analysis and optimization standpoint. There is an exercise, if you so desire, on polyNURBs. That's at the end of the polyNURB section on this part right here. You can play with it if you want. Other than that, I'm done. We'll keep the session open for any questions, but I appreciate your time. It sounds like Darius has probably got some things he wants to say as well, but I'll wrap up my portion by saying I appreciate your time. I hope you got something out of this, and go forth and inspire.
Yeah, thank you, Eric. Yeah, and this is still the tip of the iceberg of what you can do with Inspire, but it should be the catalyst to move forward. One thing I want to add, so if anybody's from a competitive team and you have a sponsorship, you get the full version. You don't get the student edition of all the products. So that way, there's some, there's no limits. Inspire, while the student edition does not have a constraint on number of nodes in it, the student version is of the 2017.1 version, while the latest version is 2017.3.1. And there's a couple additional features like in polyNURBs that Eric had, while in the student version it's not there. So we do strongly suggest sign up for the sponsorship. It's again, you get our software, you develop a better relationship between your organization and Altair. You get some technical support and then just even guidance of where materials are that you can use. So it's a big benefit. We're here to help, and in this one of those cases, if you don't ask, you're not going to get help. But in this case, we're trying to be here to help you out. Again, I hope everyone did find this useful. And if you also feel that this is something that your advisor should be aware of, please reach out to us at altairedu@altair.com and let us know, and we can work with you to arrange a special training session for any sponsor team and their advisor. Like this, web-based, or if you are close to one of our offices or application engineers, we will do our best to try to meet you at your location. Of course, it's a little hard if you're in the middle of Nebraska. We don't have anybody out in that area, so that would be a hard place for us to get out to. So yeah, we'll stay on till about 5:30, and if there's no questions at that point, we will close the session and go from there.